Some functions have domain restrictions because particular values for the input variable cause the function to become undefined. We have three examples of that displayed on the screen. Each of these functions has a domain issue at x equals 2, mainly that we have 0 in the denominator. So for f of x, g of x, and h of x, each one of them behaves quite strange at x equals 2. Taking a look at f of x, we can see a missing point that corresponds to x equals 2. G of x has two missing points. Our function has a disconnect at x equals 2. And h of x has a vertical asymptote at x equals 2. Our function gets infinitely close, but never actually crosses over that vertical asymptote. Let's take a look at each one of these functions individually and understand a little bit better what we can say about what the function does, what the behavior looks like right before it hits this strange point on the graph. For the function f of x, we could imagine a point on the function that we can slide around. So I have 2 points on the graph. They're both in green. One is left of x equals 2, and one is to the right of x equals 2. We're going to drag each of these points along the curve and watch what happens to the function outputs. Now remember, we describe inputs with the horizontal value, and we describe the outputs with the vertical value. So in this case, as that point slid to the right towards the x equals 2 location, the outputs increased to be equal to about 4. We can say that the behavior of the function is tending towards the value 4, even though f of x is not defined at x equals 2 at all. It's not equal to 4, the function itself, but the limit is tending to 4. So we can say as x is approaching 2 from the left-hand side of 2, that our limit for the function f of x is equal to 4. The notation that we use starts with LIM. This is the indication that we're applying the limit operator. Our input variable x points with an arrow towards the value 2. This is what we're allowing our input to approach. And then we have a little superscript. It looks like an exponent. That's a negative symbol. It's not really an exponent. It is a superscript telling us that we were approaching 2 from the left side of 2. Let's repeat the same investigation, but for a point that starts off on the right side of 2. So we'll drag that point along the function, and we see that it goes to the same location as the last point that we investigated. So we can say as x is approaching 2 from the right side of 2, that the function outputs are tending to 4. So in this case, our limit notation is very similar. In fact, it's equal to 4, so super similar. But notice that the superscript on the 2, on the value that our input variable is approaching, it's a plus sign, not a minus sign. This indicates that we were investigating points that were on the right side of 2 to determine what the function's behavior looked like. Now here, notice that our left and our right limits are equal to each other. The left limit is 4, the right limit is 4. So we really don't need to specify whether we started on the left or the right-hand side of x equals 2. We could generalize and say as x is approaching 2 from either side of 2, our function outputs are tending to 4. Notice that for this two-sided limit, the limit where we don't specify if we're starting from the left or the right because it doesn't matter, there's no superscript on the 2. X is approaching 2, and we do not indicate if we started on the left or the right because we're saying it doesn't matter. You get the same result no matter which side you started on. This function has a two-sided limit because the left and the right side limits match each other, but not all functions have that property. Let's take a look at g of x. We'll start with 2 points on the function, one on the left of 2, one on the right of 2, just like before, and we'll investigate what the function outputs are doing as we allow the inputs to approach 2. Dragging the point left of 2 towards x equals 2, we notice that the function outputs are consistently -1. So the left-sided limit, when x is approaching 2, for the function g of x, It's equal to -1. The output of that green point is being sent to -1. What about traveling towards 2 from the right side of 2? This point is consistently producing outputs of +1. The function behavior is telling us to go to this location. So the right-sided limit, when x is approaching 2 for the function g of x, it's equal to 1. Now again, just to reiterate, g of x is not defined at x equals 2. So we're not looking at what the function is equal to, we're looking at what the trend in the function behavior is telling us. It's telling us to head to this point, even though the function will be undefined at these 2 green points. On the last function, the left and the right limits matched, and that's not true here for g of x. The left and the right limits do not match. -1 is not the same thing as +1. So we are not able to generalize a two-sided limit. We can't say as x is approaching 2 from either side of 2, the function is tending towards one value, because it's not. It's going to 2 different places. So if we were to try and write the two-sided limit for g of x when x is approaching 2, we would say that it doesn't exist. There's not a single value that we can use to represent the function behavior for this two-sided limit. What about that function h of x that had the vertical asymptote at 2? Can we use these limits to describe the function behavior? Yes, we can. We'll start by putting points on our function and then drag them towards x equals 2 and observe what the output behavior looks like. Starting with our left point, we notice that the point just shot off to infinity. Basically, the function output values continuously grew as we slid the point towards the right to approach x equals 2. So for our left-sided limit, we would say that h of x is tending towards positive infinity. There's no limit on what these function outputs can look like. They become larger and larger and larger as we plug in points that are closer and closer to 2 on the left side of 2. And the same thing happens on the right. If we allow a point from the right to approach 2, it also heads off to infinity. So our right-sided limit for h of x, when x is approaching 2, it's also equal to infinity. And since the left and the right limits match, we can say the two-sided limit does exist and it's equal to infinity as well. Now, one thing I want to clarify here is that a function itself can never equal infinity. However, the limit of a function is not talking about what the function is equal to necessarily, it's talking about what the behavior is acting like. So this function is acting like it's sending points up to infinity, even though it never produces a point that is exactly equal to infinity.